Hello, welcome back. Let's take a look at calculus now. So, when we say calculus, we really mean two things. We mean the derivatives and we mean the integrals, right? And these aren't really two very separate things. I mean, they are separate things, but they revolve around the same idea. And in fact, they are opposites of each other, or they are inverses of each other, right? So before I get into anything, I should tell you that in this video, I will be mostly talking about the big idea behind calculus and the big idea behind derivatives in specific, right? So I will not be talking about specifically how to integrate or how to differentiate, right? But I will be talking more about the reason behind the things, right? So if you just want to see how to do the work, maybe skip to the next video. But in my opinion, it is pretty important that, when you differentiate, say, any equation, you should have a good enough idea of what you're doing, right? So briefly, let's talk about the importance of it first, because I'm sure that you have heard of it before, and I'm sure that you've looked at the index of your book and wondered why six of the chapters are about calculus, right? So the thing is, calculus is a pretty big thing. It's a major thing. And the reason behind it is that it allows us to interact with all sort of functions and graphs. It allows us to work with continuous data instead of something that may be discrete, right? So just maths aside, if I were to give you an example of physics, calculus is there in every bit of physics. Let's say there's some particle that is oscillating and you know its displacement function. How would you calculate its velocity, its acceleration? If I take bio, in bio there's say rate of growth of bacteria that would have calculus involved. In chemistry, there would be rate of reactions, there would be calculus involved, right? So calculus is involved everywhere, and that is what makes it important. And the reason why it is everywhere is because it allows us to work with continuous data. What do I mean by continuous data? Well, in real life, sorry about that. In real life, everything is continuous, everything is instantaneous, right? So it is not the case that, let's say, if a car is speeding up, so let's say this is a car, this t at time equals 0, time equals 1. It is not the case that from time equals 0 to 1 it is moving at 1 meters per second, and from time equals 1 to time equals 2 it magically jumps to 2 meters per second, and from 2 to 3 it magically jumps to 3 meters per second. In real life, there are not these sudden jumps or sudden changes. They're not steps. Instead, what happens is that there's a car, and what I mean by constantly speeding up, right? So if the car has a constant acceleration, what it really means is that at the start, its velocity is continuously increasing at every instant. So first it speeds up a bit, and then it increases, continues to increase. Right. And this is what calculus allows us to work with, and this is why it is pretty important. Right. So now let's talk about derivatives. Right. So let's say this is my road, and let's say this is my car, right? So, and also let's say it is, for the time being, let's say it is continuously moving at 2 meters per second, right? What continuously moving at 2 meters per second means, it means that for one change in for every 1 second there is 2 meters change in displacement, and this is continuous, as in this is linear. It is a constant rate, right? So for those who don't know, velocity is the rate of change of displacement. So delta S over delta T. Delta basically is a Greek symbol which means change, right? And S is often used for displacement, T is often used for time. So the rate at which displacement changes, i.e., how much change of displacement was there for a certain change in time, is how we define velocity. And so if I, let's say, take S over here, T over here, take V over here, and then, sorry, take time over here and velocity over here, You would agree that velocity is constant for all times, so this is constant at 2 meters per second, and you would also agree that the displacement time graph would be a line like this whose gradient would be 2. Right? So what does the gradient mean? The gradient means the change in x over change in y. Right? So if I take this particular point, let's say this is time equals 1, and at this point the displacement was 2, right? And let's say I take this point, and let's say this time equals 2, this was 1, and let's take 4. Right. So if I take this 1 to 2 region, if I take this portion, right? So since this is a straight line, I what I could do is say that, for this much change in time, the corresponding change in displacement was this much. Right? So gradient would be the change in displacement over the change in time, which in this case would be 4 minus 2, right? So 4 is the upper value, 2 is the lower value, 4 minus 2 over 2 minus 1, right? So delta S can be represented as S final minus S initial. Delta T can be said as the T final minus T initial, right? So 4 minus 2 over 2 minus 1, this is 2, and this agrees with our fact that velocity is constant T2, right? So your gradient is the change in x, the change in this y value over the change in x. How much y changes with a particular change in x, right? So this was an easy example. Now let's take an example where calculus would be of some use, right? So let's take this car, and let's take some sort of a real life example. Let's say this car is initially at rest. It speeds up, so it's moving at slower speed initially, then it speeds up to a maximum value over here, and then it slows down. So speeds up, slows down, right? So just again, because that wasn't so smooth, speeds up and then slows down, right? So initially it's moving slowly, speeds up to a maximum value and then slows down, right? So let's take displacement on the y-axis. Actually, let's make a better graph. Let's take displacement on the y-axis, time on the x-axis, and let's take velocity over here, time over here. Right. So one thing you would agree that, the velocity time graph sort of looks like this. Sort of looks like this. Right. I'm satisfied with this. Right. So at some time t, it has reached a maximum value, and initially at time t equals 0, its value was 0, and at the final stage its velocity is also 0, right? So this sort of makes sense that its velocity time graph would look something like this. Right. So let's come over to the displacement time graph, right? So displacement time graph initially, since velocity is very less and velocity being less means there is less change in y over change in x. So for this much horizontal change, there is less vertical change, right? So initially it is a more flatter line, right? So it starts out with something like this, right? This is time, right? And let's say this is some time t at which it has reached a maximum velocity. So it starts out as more of a flat line, and then it increases, then it reaches t, and at this point it is the it is the steepest that it has gotten. The reason being that when velocity is the maximum, there is the most change, there is the most vertical change for a particular horizontal change, right? So there was this car, it speeded up to its maximum value, and after that it is slowing down, right? So let me select this car, and actually let me make a new car over here, right? So after it after it reaches maximum value, right? So here it reaches maximum value. Now it will slow down. If it is slowing down, then that means it is covering the lesser displacement for a specific time period. So there is more horizontal movement than there is vertical, or there is more change in x as there is change in y. So the graph flattens out and it reaches this horizontal line, right? So the relation between velocity, so actually this graph, right, when you look at this graph, you would have to agree that this graph is a gradient of this graph at every point. What I mean by that is, velo let's call this graph 2, let's call this graph. And what graph 2 is basically doing, it is looking at every point, right? And it is looking at its gradient, right? So t equals 1, let's say it gives some, it right, so what does gradient at a point mean? Gradient at a point basically just means it's tangent at that point, right? So what graph 2 is doing, it is taking different points and it is and the y value that it's inputting over here is actually the gradient of this line, right? So let's say time equals 1, this gradient of the tangent turned out to be 2. So at time equals 1, this y value will be 2. And this does it for every point on this curve. So it is taking the gradient at every point and it is plotting it over here, and hence we get this velocity time graph, right? If I scroll up to here, this is what happened here too, that it was taking every point, and in this case it just turned out that every point had the gradient too, right? So when I say point on a gradient, you should be asking a question that how can a point have a gradient, or in this particular example, what is the concept of instantaneous velocity, right? So actually, when we say instantaneous velocity, it is sort of a flawed concept, right? So if I give you a video of a car, you could calculate its velocity, right? Because you would know how much its displacement changed with a certain change in time. But if instead I gave you a picture of a car, you won't be able to tell its velocity because there's just a car in an instant, right? So here's what we really do when we differentiate it. So a derivative is the best approximation of gradient at that point, right? So let's take a graph as an example, right? If I want to take the gradient at this point, I'm basically just asking the gradient of this tangent, right? So let's take this point P and let's say I take this point Q. And if I try to do change in x over change in y, so this would be change in x, this much would be change in y. That would be, you will realize that that's sort of an unfair representation, right? Because this curve is not really equal to this line. There's an evident difference that we can see. So let me duplicate. Oh, oops, I deleted it. So let me duplicate it. Let's put this here. So let's take the same point P, and instead now what I'm going to do is I'm going to move Q closer to P. So let's take Q over here, right? So now if I draw this line and I try to take the change in X over change in Y, I mean, you can still tell that this is a line that is not equal to this curve, but what you realize that compared to our first model, this is a better representation, or this is more closer to the tangent at point P than is the one in our first model, right? So just to make the relation even clearer, let's duplicate this, put this over here, and let me take point P over here. And now I move Q very close to P. Right? So this is Q. And now I draw a line. So from P to Q. What you realize is that as Q is getting closer and closer to P, the line that you get, or the gradient of the line that you get, will be closer and closer to the tangent, right? So this is the tangent. So as I'm taking, as my q is getting closer and closer to p, or in other words, as the change, so, oops, see, it's very zoomed in, so it's hard to draw p. So as my change in x that I'm taking is getting smaller and smaller, and of course my change in y would also be getting smaller, but as I'm taking smaller and smaller change in x, the result that I'm getting is closer and closer to the actual value, right? So this is what calculus, this is what derivative does. This is at the heart of derivative. So what derivative really does, it's asking the question that what is the value of this gradient approaching as your change in x is approaching zero, right? So as your change in x is getting smaller and smaller, what is this value of gradient that is approaching, right? And so by using this clever technique, differentiation allows us to find the gradients at specific points, the gradient of the tangents, right? And so we can work with functions like these. So the differential of the displacement time graph gave us the velocity time graph, right? So now convince yourself why the differential of the velocity time graph should give us the acceleration time graph, right? And that's all for today. Bye bye.